Okay, good morning. Let's get started. Little orientation about the final project. Hopefully most of you submitted your ideas for final project last night, along with a couple of screenshots or a short video demonstrating implementation of milestone 1. Yes? Good? Okay, awesome. All right. So, keeping with our regular cadence of submitting something every Monday night, next Monday night you will be submitting a little bit of text directly into the Brightspace submission, reminding the TA and myself of what you're working on and what you're demonstrating in milestone 2. So we're not going to remember what your project is and what your 4 milestones are. You can copy and paste from week to week. What a surprise. You're working on something that you've never worked on before. Maybe some of your milestones were a little too ambitious or not ambitious enough. If you change your milestone, just let us know. I'm submitting milestone number 2, and as promised last week, this would be the lower half of a biped, but I've been struggling with the knees and ankles, so I've implemented the knees and ankles differently, as you can see in the accompanying screenshots and or short video. Something along those lines. A few sentences. Please no essays. We've got 60 students submitting 60 project ideas. The TA and myself are trying to follow along with you. So as you're writing up and submitting your milestones, keep in mind that you're writing it for us, so try and make things easy on us. Okay. Any questions about final project, milestones? All good? Okay, just a reminder, so I forgot to mention this, an advertisement for tomorrow. SWIX and the CS crew are putting on CS course review night. None of us professors are allowed to go because you're going to gossip about what courses are awesome and which ones are maybe not so awesome. Obviously, we know which is the most awesomest course offered by the computer science department. You're participating in it right now. Allow me to add my own advertisement for a graduate seminar that I teach. I teach in the fall. This is Mind Morphology and Machines. You might remember at the very beginning of this course, we talked a little bit about Descartes and this idea of Cartesian dualism. There are a lot of ideas that go back hundreds of years, arguably thousands of years, that influence the way we think about trying to create intelligent machines, machines that are smart, machines that think, machines that understand, machines that are conscious, maybe, yes, no. If you're interested in the philosophical aspects of all of this, and you're here next fall, consider signing up for Mind Morphology and Machine. If you want to find out about all the other courses that are not as awesome, please check it out tomorrow night. Okay. All right, back to this course. We are working our way through open challenges in the field. We looked last time at neat and hyperneat, 2 algorithms that have a relatively complicated way of taking a genetic blueprint and turning it into a phenotype, which in our case is typically a robot. We're going to switch and start tackling today arguably the biggest and most important open challenge in the field, which is crossing the reality gap. You have all now started to evolve interesting and fun behaviors for your quadruped. How easily do you think it would be if you had access to the Fab Lab over in the Vody building to actually build a version of that quadruped and download some of these controllers into that quadruped and have that physical quadruped do what you see your virtual quadruped doing? Chances are probably pretty low, right? Why? Why is it so difficult to take something from simulation and transfer it to reality?
Well, I mean, you have to use a microcontroller to code all the motors. You have to figure out a source for power. You have to figure out what kind of sensors you're going to use and make sure you have enough pins.
Yep.
Are you going to put a breadboard inside of it?
Yep.
I guess that's kind of it. But
and on and on and on, right? Yeah. Breadboard, batteries, wires, pins, Raspberry Pi, all sorts of things that aren't in the simulation, right? A simulation, by definition, is not real life. If it was, we'd just do everything in real life. The whole point of the simulation is to paper over a lot of the annoying details of real life, which is great for you all because you can sit with your laptop and code things up and evolve behaviors for robots. But the ultimate goal is actually to have intelligent and safe machines that operate alongside us here in the real world, we're going to have to cross the reality gap somehow. So how do we do that? Maybe we start building into the simulation breadboards and circuits and pins and all the other wires and all the other nitty-gritty details we need. That's one possible approach. Seems obvious, a way to go. What's the problem with it? Why don't we just keep making more and more accurate simulations?
We're already at least semi-limited by compute, and the more that you bake into the simulation right at every step is just going to exponentially drive that up.
Absolutely. So the more we put into the simulation, the slower it's going to run, the more compute it's going to need, the slower things go. So the most intuitive solution to crossing the reality gap, make a more accurate simulation, is problematic. So what else can we do? Roboticists have been thinking about that and proposing ideas for a very long time now, and we're only going to have time to look at 1, 2, 3, 4 of those approaches. And we're going to start today in lecture 14 with the oldest and the original approach to solving this problem, which has a very long name, the radical envelope of noise hypothesis. Okay, this idea, this original solution was proposed a long time ago, and like a lot of things in machine learning, the machine learning community rediscovered this solution. So in 2018, NVIDIA breathlessly announced this whole new approach they had to robotics, which is if you wanted to train or evolve a robot arm to do the place the cylinder in the hole problem. It's a little difficult to see here, but you might notice that there's a robot arm, and at the end of the arm it's holding a string, and at the end of the string is a little yellow cylinder, and the idea is to train an arm to be able to take the cylinder and drop it into the slot in the blue cube. Tricky to do. So NVIDIA said, listen, we're making these whiz-bang new GPUs that have a lot of computational horsepower. Why don't we train controllers for this robot arm to solve this problem? And we're going to run a whole bunch of these different controllers on a whole bunch of different simulated robot arms. So if you look carefully, you'll notice that all of the blue blocks here are slightly different sizes and geometry. Same thing with the cylinder. Although you can't see it in this picture, the string that the cylinder is hanging from is a little bit stronger, a little bit weaker, a little bit thicker, a little bit thinner. So NVIDIA's brand new idea in 2018 was, let's add a bit of noise in the simulation. Every time we simulate a robot and let a controller control that simulated robot, that controller is always going to be controlling a slightly different robot in a slightly different environment. Unbeknownst to NVIDIA, this idea had been proposed a very long time ago, back in the late 90s. So let's go through this idea. At that time in the late 90s, a group of roboticists made the following observation. The field of evolutionary robotics was just getting started. And it was very quickly realized that, and you've probably realized this as well now, evolved controllers will exploit details of the simulation. Have you noticed that in your own work? In what ways is your parallel hill climber starting to evolve things that are not quite realistic about your physics engine? When you've evolved controllers for the quadruped or for the original 3-link robot and you played it back, were you amused sometimes? Were the solutions not quite what you were expecting? How so? I'm sure you've seen some. Perverse instantiation is ubiquitous. You're now evolving the quadruped to move as quickly as possible. One of the things that's difficult about moving quickly is when you drag parts, friction slows you down. Easiest way to overcome friction? Jump or prong. Most quadrupeds are not strong enough to actually get their body weight off the ground. Somewhat realistic, it's possible, but tricky. Some of you might have gotten the stuttering shutter, where the robot shifts its motors back, clicks its motors back and forth very, very quickly and manages to move that way. Tricky for a robot to do that in reality because parts have mass and momentum and inertia very quickly to reverse course. You can do it on a robot in some cases, but it's very, very expensive to do. I started using physics engines back in 2001, and at that time the physics engines were a little buggy, and I evolved a robot that would push two of its links together so that they would start to interpenetrate. And when two objects interpenetrate that aren't supposed to interpenetrate, what does collision detection and resolution do? It starts to apply a counteracting force. But if that collision resolution algorithm can't resolve the collision, if at the next time step those two objects that are not supposed to interpenetrate are still interpenetrating, what does the collision resolution algorithm do? It starts to apply more force. So I inadvertently ended up evolving robots that would push parts together and together for a while and then explode and travel 1,000 length units in the distance that they're supposed to travel. Perverse instantiation. Happens all the time. If you haven't seen it that much yet in assignment 10, I guarantee you in your final project, whatever it is that you're doing, you'll see it. So we've got this problem. We're going to start with this problem. Artificial evolution will create controllers that exploit details of the simulation. And if those details don't exist in reality, then of course, if you take that evolved controller, which is exploiting the simulation, and drop it into reality, you're going to stumble over the reality gap. You're not going to get a transferal. Okay, so how do we deal with this observation? Well, we could try and poison the simulator so that there's no way for evolution to latch on to behaviors that exploit particular details of the simulation. In the buggy robot that I was just telling you about, the collision resolution algorithm was not random, it's deterministic. It always does the same thing. So if that robot always pushes two links together, the robot's always going to explode. That's a reliable phenomenon that the evolutionary algorithm can rely on. So the idea here was, let's make every single simulation unique. Everything's a little bit different from one simulation to the next. So evolution cannot rely on some of these specific artifacts. Okay, so we're going to have to add noise to the simulator, but if we add too much noise to the simulator, if every time we drop a controller into a simulation, that simulation is completely different from the one before, if there's too much variation across simulations, then there's nothing for evolution to latch onto, and evolution won't be able to increase the fitness of evolving populations over time. So we need to somehow figure out how to apply noise to the simulator in the right way. What does that mean? It's kind of a Goldilocks type problem. We want to put a little bit of noise in the right place, but not too much noise in places where aspects of the simulation are going to transfer from simulation to reality. So far, so good? Make sense? Okay, that's the intuition. So that raises the obvious question, what aspects of the simulation would you noisify? You're all experts now on physical simulation. Have a guess. Given your simulation, given PyBullet and the quadruped, what are some aspects of the simulator that you might want to make a little bit noisy, and which ones maybe you want to leave alone? There's gravity in your simulation. It's acting at 9.8 meters per second squared downward. Should we noisify gravity? Assuming we're developing a robot for this planet, probably not. 9.8 is pretty constant on the surface of this planet. So there's an aspect of the simulation that we probably don't want to noisify. That is relatively constant here. What are some other aspects of simulation that are not so constant?
Maybe the strength of the motors.
Strength of the motors, right? We were just talking about details of the mechanical construction of a robot. You're going to build your quadruped in reality, and that quadruped has 8 motorized joints, so you need to buy 8 motors from Amazon. You order 8 motors, you build them into your robot. Those motors are going to be slightly different. You pay for expensive motors, they're all going to be relatively the same. But as you start to use your robot for hours and possibly days, those motors are going to start to experience a little bit of wear and tear. And they're going to wear and tear in slightly different ways and become different over time. So maybe we noisify the strength of the motors, causing evolution to try and find controllers for the robot that's a little bit robust. It doesn't matter too much if the motors are a little bit stronger or weaker. That controller will still reliably produce forward motion.
Well, the thing in reality that would be noisy is the sensors.
Absolutely. Number one culprit is sensors. Sensors are reliably noisy. Noisy how? It's tricky. There's a whole subfield of robotics about how to simulate sensors. It's tricky. Other aspects of the simulation that we should noisify. Motors, sensors. Friction. In this room, maybe friction is relatively constant. It's relatively high. There's rugs in here. Out in the hall, it's the linoleum. Friction is, the minute I walk outside, friction is quite different. Friction is usually a good aspect of the simulation to noisify. So you can see how we can start to go through a physical simulator and start to enumerate things that are relatively constant in the real world and not constant, and take those things that are not constant and start to noisify the simulation. Okay. However, if you think about it, the more complicated the physical simulator is, the more possible things you need to decide whether or not to noisify. You're working with PyBullet. That's sort of a middle range physics engine. It's complicated, but there are many more complicated, more complex physical simulators, which if you get them right, they're a better reflection of reality. So as the simulation becomes more complex, more things we need to think about. Friction, maybe the mass distribution of the robot. We just mentioned cabling and wires. As a robot moves around, the wires are actually jostling around the body of the robot. And depending on the size of the robot, that can actually change the mass distribution of the robot non-trivially from moment to moment. So maybe mass distribution, the specific geometry, we might not get that right. Joints and motors, sensors. This is getting complicated. We now seem to be thinking about a very complicated approach. So the investigators back in the early 90s said, wait a second. Instead of having a big, complicated, noisy simulator, why don't we just make a really simple simulator so there just isn't that much physical stuff for the evolutionary algorithm to glom onto and start to exploit if we get some of these things wrong in simulation. So you'll remember we spent a bit of time talking about minimal cognition. There's a sister set of experiments which we're going to talk about today, which are the minimal simulation experiments. And this is also known as the radical envelope of noise hypothesis. We're going to take a very simple simulator, so there aren't that many things, and we're going to noisify some of them and leave some of them alone. Okay, so a minimal simulation contains as little physical details as possible. This was written up and published in 1997. And as I've said a few times in this course, physics engines didn't arrive until the year 2000. That being said, before the year 2000, there were people that were knocking together things that were not quite physics engines, but they were simulators or models that people were using to evolve controllers. So we're going all the way back to the beginning of the field of evolutionary robotics. At that time, some roboticists like Jacobi and his team were making their own things that were still not quite physics engines, but they're on their way. And in this particular case, they tried to make a simulator that was as simple as possible. They're going to refer to the set of things, the set of things that they're not going to noisify as their base set of interactions. Your robot interacts with a downward force of 9.8 meters per second squared. That base set of interactions between the robot and the force of gravity, that would usually fall into the base set. That's something that has a basis in reality, at least on this planet, and it's relatively constant here in reality. There still might be a little bit of difference. Then there is the implementation set of interactions. Implementation, meaning it's something we've got to build into the simulator that probably doesn't have a very good basis in reality. It's kind of a hack, or it's something we need to do to simulate the robot. Okay. It might be completely different in reality. We'll see some examples of an implementation interactions in a moment. Okay. So we're going to see a relatively familiar evolutionary algorithm evolving populations of controllers, where the evolutionary algorithm takes each controller in the population, drops it into a simulated robot, calculates fitness, does that for all the controllers in the population, deletes the robots or the controllers with low fitness, and makes randomly modified copies of the surviving ones. We're going to see that, but every time the evolutionary algorithm drops a controller into the robot, they're going to sprinkle a little bit of noise onto the base set of interactions. These researchers are a little bit paranoid, probably for good reason. They don't think anything has a perfect match between reality and their simulator. So you're going to put a little bit of noise on the base set and 100% of noise on the implementation set. This seems odd. They're going to, how do you make something completely noisy? We'll see that in a moment. Okay. This robot should look relatively familiar to you. Which robot is this? It's not the Roomba, although the Roomba is based on it. Anybody remember? The little hockey puck robot. So this is the Kepera robot. We've got two, it's a big size of a hockey puck. We've got two little wheels. We've got 1 to 6, 7, 8 infrared sensors. Remember, infrared sensors send out a pulse of infrared light, and then they measure the amount of time it takes for that pulse to come back. And the longer it takes for that pulse to come back, the further that pulse must have traveled and then returned to the sensor. So we've got 8 distance sensors on board the Kepera, and we've got 2 ambient light sensors. So photosensors, one on the left, one on the right. Here's the task. They're going to evolve this robot to perform the T-maze experiment. You all know the meme of researchers in lab coats who put rats in mazes. This is where that trope comes from. So this is a very, very old experiment in animal behavior. You take a rat and you put it in the base of a T-maze. You put a piece of cheese either in the top left of the T or in the top right of the T, and you let the rat go. And as the rat moves around, if it happens to move up the stem of the T at all and passes a certain point, you flash either a light on the rat's right-hand side or on the rat's left-hand side. You flash the light on the right if the cheese is on the right, and you flash the light on the left if the cheese is on the left, and then you immediately turn off the light, and you watch to see whether the rat makes its way to the junction in the T and then turns in the right direction. This is an experiment meant to test whether a particular animal species is capable of memory. Can the animal remember on which side it saw the light and then turn in that direction to get the reward? You can do the same thing with a robot. In this case, we put our Kepera in the base of the T junction. We put a controller we download a controller into the Kepera. Sensor values start flowing to motors. The robot starts moving. If it moves past this point, flash the light. And if it gets to the junction in the T-maze and turns in the correct direction, you give it some fitness. If it doesn't, you don't. And you keep evolving controllers for this robot until every time you flash on the left, when it gets to the junction, it turns to the left, and every time you flash on the right, it turns to the right. If you're able to evolve a controller to do that, obviously that controller must have memory. It must have recurrent connections, and evolution must have tuned those recurrent connections to allow the robot to remember to which side it saw the light on. Okay, you're all experts in physical simulation at this point, and you're also experts now in embodied cognition. Obviously, memory is required to solve this task. You're all experts in me as well at this point. The answer is not. It is not that you need memory. There are other ways to solve this problem. How can a robot or an animal, for that matter, cheat in the T-maze? How can you use your body to solve the task without having to remember on what side you saw the light?
Well, the animal could use his smell.
Oh.
Smell where the cheese is.
Okay.
Go where it is.
Absolutely. So in the case of the rat, it could cheat. Again, embodied cognition, it just relies on some other sensor modality. So assuming it's good old cheese, maybe it can just smell it and associate that, some aspect of the smell with the light, and it doesn't need to, it can ignore the light altogether.
And then maybe the robot, I don't know if that would be memory, but when it goes through the light, one sensor, the ambient sensor is going to be way higher
Yep.
than the other.
Yep.
And then it can just turn, when it goes to the T, it's just going to turn where the ambient sensor was.
Where the ambient sensor is. So if you remember back to Bradenberg vehicles, right? Lights on either side. Presumably when the robot gets here, assuming it's facing more or less up the stem of the T, it's going to feel more light on the right than the left in this example. And at that moment, before the light has turned off, the robot can alter its relationship to the environment so that when the light turns off, it no longer needs to remember. The controllers could evolve, for example, that when it senses more light on the right, the robot immediately turns 12 degrees to the right and then drives straight, which means it's going to do something like this, and then it bounces off this wall and in it goes. It doesn't need to remember. Or alternatively, when the robot gets here, it turns 90 degrees, goes right up against the wall where the light is, and then, remember, it's got distance sensors, so it hugs the wall. It does some sort of Bradenberg trick to stay next to the wall. Hug the wall on which you saw the light. I don't know if any of you do this, but sometimes you tie a knot in a piece of Kleenex or you do something in the moment so that you don't forget. Then you go off and you forget whatever that thing was, and then when you reach in your pocket, you feel a knot in your Kleenex, and that's the reminder. You've left something in the environment. You've altered some interaction between yourself and the environment so that your brain no longer needs to shoulder the load of memory. Yeah? Okay, that has absolutely nothing to do with the radical envelope of noise hypothesis. It's just, if you thought of that solution, you're starting to now think like an embodied cognitive scientist. There are ways to solve problems in the world that don't just rely on the brain. See the light, remember where the light was, and then turn in the right direction. Okay. All right, so we're going to evolve we're going to evolve controllers for this robot. We've got 8, 9, 10 sensors. We've got 10 sensor neurons. They're wired up with a bunch of synapses to the 1, 2 motors. I don't remember if there was any hidden neurons in this controller. Doesn't really matter for our purposes. We're going to evolve sets of synaptic weights, and fitness is going to be defined as D1 plus D2 plus 100. Where D1 is how far up the stem of the T the robot goes. So if the robot just moves around randomly at the base of the T, it gets a very low value of D1, and those controllers very rapidly get evolved out of the population. Controllers that survive and produce offspring have higher values of D1. They tend to travel up the stem of the T. And then perhaps there are some controllers that also happen to turn when they get in the junction and start to travel some distance along the top of the T in the direction of the reward. There's no cheese for the robot, there's just variables. If it turned in the correct direction, it gets 100. If a controller travels up the stem of the T, which is good, and then it turns and travels D2 down the wrong top part of the T, it doesn't get the 100, but it still gets some reward for traveling along the top of the T. So intuitively, this fitness function is selecting for controllers that drive the robot up the T, controllers that also get the robot to turn at the junction and head in one direction or the other. It doesn't really matter which one, but we want it to also learn how to travel around the top of the T. And then if it happened to turn in the correct direction, it gets an additional 100 points. Okay. So far, so good? Seems kind of straightforward. Okay, here's the tricky part now. The minimal simulation that the investigators created is not a simulation of this thing. They created two different simulators. There's this one and this one. So phase one, this is the base of the T turned on its side, just so we can show it here. So here's the robot, and we see whether or how much it travels up the stem of the T, and if it travels anywhere in this region here, the ambient light sensors get some light. Okay, we measure D1. If D1 is large enough and the robot starts to travel into the intersection, that robot and controller are teleported out of this simulation and dropped into this simulation here, which is just the top of the T. You'll notice there's something called the noise zone back here. The noise zone back here is if any of the infrared sensors, which send out a pulse of infrared light, if any of the sensors send out a pulse of infrared light and it enters this noise zone, that pulse of infrared light comes back with some random time interval. This seems like a crazy simulation. Why? Why did they build it like this? Why are they noisifying so much of the robot's incoming sensory information when it's sitting in the junction? Anyone ever played with actual infrared sensors before? We were just talking about how finicky they are. They're pretty good if you have an infrared sensor and you're more or less facing a relatively flat surface with a uniform reflectivity. So if I had an infrared sensor here, it would work pretty well here. If I start to face more and more obliquely to this surface, the infrared sensor is going to get a little bit noisier. If I'm shooting my infrared sensor into this environment, the geometry of this is pretty complicated. Imagine shooting out a pulse of light. How or whether is it going to actually reflect and get back to me? I'm going to get a whole bunch of very noisy signals in this particular region compared to this region here. Simulating a robot that's emitting infrared pulses in an environment that may look might look relatively simple here, but there's a bunch of corners here. It's tricky. Light starts to bounce around. If the evolutionary algorithm starts to evolve controllers that rely on reliable infrared sensors in this zone, it's definitely not going to transfer to reality. So basically, any controller that managed to drive the robot into this zone starts to experience very, very noisy sensory information. And if this controller is going to successfully turn the robot in the correct direction, that controller should more or less ignore its noisy input at that time and turn based on either some internal information or possibly don't turn at all, just drive straight through this region and get out of this region and then start driving again in response to sensory information. We haven't talked about how a neural network controller can actually do this. You can try and evolve it for yourself. If it turns out you can evolve controllers in which sometimes that neural network controller is relying on the sensor values coming in, and sometimes it effectively ignores those incoming sensory values. The neural controller needs to do that by, in this case, it does need a little bit of memory. It needs to see that sensor values are jumping around a lot from one time step to the next. If they're jumping around a lot, then the internal information basically buffers out or cancels out all that incoming sensory information. Okay. Okay, so far so good? Okay, let's look at this actual simulation itself. I described it as these two different tunnels or parts of the T-maze. The simulation itself is actually a spreadsheet. This is 1997. They didn't have physics engines yet. This is about as simple a simulation as you can imagine. They had two tabs in the spreadsheet. They had two lookup tables. The first one, in table 1, the controller would look up in the spreadsheet. It would look up the robot's current orientation. How is it angled inside the tunnel? And if the motors were driving the robot forward, the controller would look at the two values that were currently sitting at the two motor neurons, and it would update the robot's X and Y position. So a little bit of trigonometry here. Get the angle the robot is facing, get the two values of the motors, and update the new X and Y position of the robot. That's what's in the lookup table. So basically, 3 columns. The first column is the robot's orientation, the angle. The second column is a potential motor neuron value, and the third column is the second potential motor neuron value. So at every time step, the controller would say, okay, my orientation is this, and my two motor values are this. I've got 3 floating point values. I go into the spreadsheet. I find whatever row most closely matches those 3 values, and I look at column 4 and 5, which give me the change in X and Y. What should my new X and Y value be? Everybody see that? Very, very simple. So they could update change in orientation and change of position of this robot by propagating sensor values through to the motor neurons, go to the spreadsheet, get the new X and Y, update the new position of the robot, get the new sensor values, and on and on. Okay. What are the sensor values? The sensor values to plug in, yes?
I mean, are you using an accelerometer to figure out the angle?
Of the robot, no. There's no accelerometer because there's no simulated accelerometer, there's no physics engine, there's no nothing. It's just the current angle of the robot.
But how are you measuring that?
Yeah, so if I'm here and my new X and Y is this, then I update my orientation as well. The spreadsheet tells me, the controller says the robot starts at X equals 0, Y equals 0. I'm facing this way. I go to the lookup table. It gives me the new X and Y. My new X and Y is this. Therefore, I know what my new orientation is.
Like hard-coded values.
It's all hard-coded. It's a spreadsheet. This is as simple as you can imagine. I'm at 0, 0, and the spreadsheet tells me my new XY is this. My orientation hasn't changed. Yeah? Okay. Okay. How do we know what the sensor values are, however? Okay. So again, the controller knows what the robot's current orientation is, theta. How is it angled inside the tunnel of the T? And how far away is it from the wall? How long is the line segment from the front of the robot to the wall? How long is this line segment? That's the value of the distance sensor. If the robot moves like this, if the orientation is this is the length from the wall. So this second table includes a lookup table, which is this distance. They're hard coding values of the infrared sensors as a function of where's the robot relative to the wall, what is the robot's angle relative to the wall. Make sense? Okay. Okay. All right, that's it. We've got these two lookup tables. We've got our controller, which is a bunch of synaptic weights. And when we quote unquote simulate the robot, we set the initial X, Y, and theta, the initial position and orientation of the robot, and start updating X, Y, and theta based on table 1, table 2 of the lookup table. And as the robot quote unquote moves around, we're going to sprinkle a little bit of noise on things that are more or less reliable. So how the robot moves in response to the motor signals. I just told you in table 1. In table 1 here, the controller takes the two motor values, goes to the lookup table, and gets delta X and Y back. When the controller pulls delta X and Y out of the table, they put a little bit of noise on those delta X, delta Ys. They're simulating the fact that motors in reality are not perfect. For any given pair of motor neurons, the change in XY is never always going to be exactly the same. Man never enters the same river twice. Okay. They put a little bit of noise on how the infrared sensors respond when the robot is anywhere other than in the junction. In the junction, that's going to be an implementation detail. That the evolution should not rely on, but evolution should rely on the infrared sensors when the robot is down here or in here or in here. Okay. We're going to put a little bit of noise on how the ambient light sensors work. If the light flashes on the right, most of the time, the right-hand light sensor will fire more strongly than the left-hand light sensor. The difference won't always be exactly the same, but generally speaking, one will be brighter than the other. And intuitively, the controller is going to have to respond somehow to that difference. If we put 100% noise on the two values of the light sensors whenever the robot was in the presence of the light, the controller has nothing to evolve to latch onto. It cannot solve this problem. Yeah? Okay. Implementation set. These are aspects of this simulation, this task, this robot that we know a priori evolution should not exploit. How the infrared sensors are going to behave when it's in the T-junction, 100% noise. The sensor may never respond. The sensor may, in effect, report infinite distance, or the sensor may report zero distance, and everything in between with uniform probability. That's 100%. That's a 100% noisy sensor. Okay. Okay. Some other aspects of the quote-unquote simulation that they changed is the side from which the light comes. If we were to evolve this population of controllers and during the entire evolutionary run, we only ever flash the light on the right, the controllers don't have to evolve to pay attention to the light. The controllers could just evolve to always turn the robot to the right. So as we're evaluating controllers, sometimes we're going to flash the light on the left, sometimes on the right. When we flash on the left, it should turn to the left. When we flash on the right, it should turn to the right. They're going to alter the width of the corridor. They're going to alter the values that are embedded in the lookup table so that from the robot's perspective, it feels as if it's in corridors with narrower widths or wider widths. When they start each controller in the simulation, they're going to place the robot at the base of at the bottom of the base of the T, but they're going to start the robot pointing minus 22 degrees to the left, 22 degrees to the right. The robot is never always going to point right up through the T, so they're varying the initial conditions that the controllers are going to experience. They alter the length of the light zone. When these experiments are done with rats, traditionally there would be a little sliding door in the wall of the T, and they would slide the door open, the light would come through, and then they'd slide the door closed. You can think of the width of that door or the width of that aperture as the length of the light zone. How much time or how much distance can the robot move and still sense the light? The length of the corridor, how deep is the base of the T? It can range between 40 and 60. So way back in 1997, they were starting to evolve controllers on robots, and they were assuring that every time that controller dropped into a robot, that controller never experienced the same river twice. Many things were changing in its environment, and some things, like sensor behavior in the junction, would change wildly. Yeah? Very, very simple simulator, but a noisy simulator. Okay. We do have details about the neural network controller for the robot. This is showing you the neural architecture. So we've got IR0 over here. So this is the left-hand infrared sensor. All the infrared sensors through here. Here's the 6 infrared sensors. Where's 7 and 8? It's not on here. 7 and 8 are not on here because we're looking at an evolved controller. This evolved controller evolved synaptic weights. The weights that were leaving the 2 back infrared sensors dropped closer and closer to 0. Evolution basically turned them off. So this evolved controller did not rely on the 2 back infrared sensors.
If you created this first without a noisy input, and then you did like a secondary training set with a noisy input, would it just evolve to have a filter?
That's a great question. That would be a perfect A/B test. Yeah. Evolve a robot in a simulated, in a noisy simulator. What kind of evolved behaviors do you get back? Then do the same thing, but evolve controllers in a non-noisy simulator. Then expose them to a noisy simulator and continue evolution. Which one produces more robust behavior, less robust behavior? Do you get different behaviors? I don't know the answer. That would be a great thing to try. Okay, so we're looking at an evolved controller here. This controller has evolved to ignore the 2 back infrared sensors. You can see connections to the 2 ambient sensors here, and there are no hidden neurons in this experiment. You'll notice bilateral symmetry was imposed. So these researchers decided they wanted to have a symmetric controller. Dashed arrows represent inhibitory synapses. Remember that an inhibitory synapse, the stronger the presynaptic neuron fires, the more it inhibits, or the more negative value it contributes to the postsynaptic neuron. Most of the synapses in you are inhibitory. Solid arrows represent excitatory links or excitatory synapses. In an excitatory synapse, the stronger the presynaptic neuron fires, the more strongly the postsynaptic neuron fires. Okay, the numbers here, which are a little hard to read, these are the activation thresholds. They're details about the activation function. They're not relevant for us. Turns out that this particular evolved controller apparently didn't take this class and doesn't understand about embodied cognition. This evolved controller does not cause the robot to quote unquote turn and hug the wall and then turn in the direction of the wall that it's hugging. This controller actually does evolve to remember on which side it saw the light. How? You're all experts on neural networks as well now. Where is the memory of the light? Often when we've done this before, it's kind of hard to see.
In the recurrent connections up in
Which ones?
the top two, like
So there's some up here.
that.
There's a self connection. This is a self connection for IR exclamation point. This is supposed to be IR1. I guess that's a typo. There's a self connection here and a self connection here, which is fine. It's kind of remembering previous infrared sensor values. It's basically mixing the current value of IR1 with the previous value of IR1. Here, this particular part of the neural circuit is the memory component. Usually when we look at a neural network, it's next to impossible, if not impossible, to see which part of the network does what. This is one of the few cases where you can. How is it that these two recurrent connections are holding the memory of the light?
They're bilaterally symmetrical, so
They're bilaterally symmetric. Yep.
they get a value and then they're just passing that same value back and forth.
That's a good idea. Possibly they're kind of juggling. They're kind of passing the value back and forth. Not quite. Note that these are dashed lines, so these are inhibitory connections. Let's imagine a single time step in which the light happens to be on the right. That means that ambient 5 is firing more strongly than ambient 0. This neuron has a higher positive floating point value than ambient 0 over here at that moment in time. Imagine at the next time step the light is turned off. Suddenly the current value of ambient 0 and ambient 5 both drop to 0. How is this mutual inhibition here? This one inhibits this one and this one inhibits this one. How does that hold on to the memory? These recurrent connections allow it to mix past values with current values. I just told you that at the current time, both sensor values have dropped to 0, but that 0 is being mixed with the non-zero values from the previous time step in which the light was turned on, and these two neurons have non-zero values. If we go back to the previous time step in which ambient 5 was firing more strongly than ambient 0, they're inhibiting each other. So you've got a tug of war between these two, but one, ambient 5, is currently stronger than the other one, which means it's inhibiting the other one more strongly. It's pushing the other one down. The other one, in turn, is trying to inhibit the other one, but it's weaker. Therefore, it's less successful in inhibiting the other one. What happens in that case? You get a bit of a feedback loop. If this is a strong value and the other one is failing to inhibit it, it's going to stay high, it's going to stay strong. This mutual inhibition circuit, this is found throughout nervous systems in the animal kingdom, including you. You have tons of these kinds of mutual inhibitory circuits in your central and peripheral nervous system because it's a very elegant way to hold on to information. If there's a brief moment in time in which there's a little bit of an asymmetry, I can see someone walking out in the hall right now, there's a little bit more motion here than here, but then suddenly it goes away. I can remember that there was motion over there because one part of the circuit, the motion circuit, is trying to inhibit the motion circuit on this side, pushes it down, and then it wins this tug of war. It's inhibiting the other one is not able to inhibit, so one goes high, the other one goes low, and they stay like that. The stronger one is continuing to push the other one down, and the other one cannot bring down the other one. You can code this up in Python if you like and actually play around with this mutually inhibitory signals. It's a very easy way to hold on to a brief piece of information that is there and then gone. Okay. All right. Again, we're at 1997 here, so I apologize for the quality of the graphics here. Hopefully you can see what's going on. This was the very first successful crossing of the reality gap in robotics. What we're looking at is a physical Kepler robot about the size of a hockey puck, and they built the T-maze on the top of a table, turned off the lights, and they put a little LED Did LEDs exist in 97? I don't remember. Whatever. They put a very, yes. So there was a little LED on the top of this robot. And as the robot moved, they did a little bit of motion cap. They did a very slow release and got a time-lapse image of what the robot did. The robot starts here. It's pointing up the base of the T-maze. It starts to move. The flashlight is turned on and then turned off again. The robot exhibits no noticeable change in its behavior. So at this moment in time, it's hard to know whether the physical Kepra that's being controlled by a controller that was evolved in the simulator, it's hard to know whether this controller has actually attended to or paid attention to that information. But when it gets to the junction, it does turn to the left. They take this, while the time-lapse image is being taken, or is being recorded, they take the physical Kepra, put it back at the base of the T-maze, let the evolved controller control it again. They flash the light again on the left, and the controller again caused the robot to turn to the left. So if you squint carefully, you should notice that there's several light paths in this image. The robot is reliably remembering on what side it saw the light. They took the exact same evolved controller, did it again, but now they flashed the light on the right, and that same evolved controller reliably turned the physical robot to the right. It's working. They successfully evolved something in simulation and transferred it to reality. This controller is not learning, it's not being trained, it's not being further evolved in reality. This is what's now known as zero-shot learning. The controller has been taken from simulation and exposed to a new environment, the real world. And with no learning whatsoever, it does the right thing. Not only does it do the right thing, but if they go in and replay that evolved controller again several more times, but now they make the corridor wider, the robot still does the right thing. You'll notice that the variation in its movement as it moves up the stem of the T is a little bit more diverse, which indicates that the robot's motion is being affected by the infrared sensors that are reporting distance from the wall, but it still does the right thing. The investigators are kind of showing off here. They're showing that not only can they transfer from simulation to reality, but they can transfer this controller between different realities, different T-mazes, and the robot still does the right thing. Here they're making the corridor even wider, and the robot still does the right thing. You'll notice there's two initial sets of trajectories. They place the robot in the base of the T-maze, pointing up and to the right, and sometimes they place the robot at the base of the T-maze facing up and to the left. So the controller is also robust to the initial conditions of the robot. Where is the robot relative to the environment when the evolved controller is turned on? Okay, I'm going to turn the lights back on. Okay, not bad for 1997. Okay, what's the problem with this? Why don't we still have physical simulators that are lookup tables, spreadsheets? Why are you using PyBullet rather than spreadsheets? What's the disadvantage or the drawback of this approach? What if instead of a Kepra robot, you wanted to have a quadruped or a biped walk down the corridor of the T-maze and then turn in the right direction? I don't know how to encode that in a whole bunch of tabs in a spreadsheet. Maybe you do. Gets tricky. This minimal simulation trick works for simple things, but it's pretty hard to scale up. So 3 years after this paper was published, physics engines started to flood the robotics market, and people started working with more complicated physics engines. But still, with these more complicated physics engines, the reality gap is not trivial. How do we know what to noisify and what not? So we're now going to switch to the Golem project, lecture 15 here, which was published 3 years after the radical envelope of noise hypothesis. The Golem project was published in 2000, right when physics engines were coming out, and ended up on the front page of the New York Times. The New York Times reporter breathlessly reported on this robotics experiment that there was now a robot that was making its own robots. Seems odd. What's going on here? I've just told you that in the Golem project, they were making use of a physics engine. So as you're going to see in a moment, you're going to see something that looks very familiar. They're going to evolve controllers for robots in simulation and then transfer them to these physical robots that you see here. Have a careful look at the body of the robot. Who built this robot? How was it built? This robot was not built by any person, it was built by a machine. In the Golem project, they were evolving not just controllers for robots, but they were also evolving the bodies of these robots along with the brains. And so they now have a population not just of different controllers, but they have a population of different bodies. So if we take some of these evolved bodies and brains and want to bring them to reality, we're going to have to ask a mechanical engineer to build a whole bunch of different bodies. Not to build just one physical robot, but build a bunch of different robots. I'm showing you just one robot here. That's a tall order for any mechanical engineer, no matter how talented they are. So the investigators in this case sent these evolved robot bodies not to a human mechanical engineer. They sent them to a brand new thing called a 3D printer. The 3D printer printed this body, and then they downloaded the controller into this robot. So there were two new pieces of technology that were used in this experiment: physical simulators and 3D printers. Apparently, from the perspective of this New York Times reporter, the 3D printer is a robot, which, if you think about it, is actually kind of accurate. So you've got one robot, a 3D printer, that's making another robot. Okay, the end of the world is nigh. We've got robots making robots, right? Skynet is nearby. Okay, that's the Golem project. Okay. We're going to talk, I think next week or the week after, about actual self-replicating machines. A 3D printer that makes a little shuffling robot, not quite self-replication. We will talk about self-replication shortly. Okay. How are we doing for time? We got 13 minutes left, so we'll introduce the Golem project. The Golem project is made up of the experiment is made up of three separate phases or steps. Step one, we're going to evolve a robot to locomote in simulation. Should be very familiar by now, except the genetic encoding of the robot is going to encode instructions about how to build its body and brain. Step two, evolve until you get a robot with high fitness that moves as far to the right as possible. Take that evolved body and brain, send that as a blueprint or a set of instructions to a 3D printer, manufacture a physical version of that robot. 3D printers back then were relatively primitive. They could only print plastic. So we're going to print basically the plastic skeleton of the robot as evolved by the evolutionary algorithm. And then they're going to snap in to this partly manufactured physical robot all the things that 3D printers couldn't print at that time, like motors and electronics and batteries and sensors. Now, 25 years later, 3D printers are getting pretty sophisticated, and there are now 3D printers that can kind of print motors, can kind of print batteries, can kind of print electronics. They're not great. We're getting very close to the point where a 3D printer can print the entirety of an autonomous mobile robot and have that robot walk out of the 3D printer. It hasn't happened yet, but it's going to happen very soon. Okay. All right, that's a 10,000-foot view of the Golem project. Let's start with phase one, the most familiar phase for us. We're going to set up an evolutionary algorithm to evolve robots to move as fast as possible. We just finished talking about the G to P mapping last time. In the Golem project, they used a relatively complicated genotype to phenotype map as well, because the genotype has to now encode more stuff. The genotype is now encoding not just a set of floating point values, which specify the weights of the synapses in the controller. The genotype is going to have to encode a bunch of other things, like the bars that make up the robot, the aspects of the connections between these bars, what's happening where these bars meet. The genotype is also going to have to encode aspects of the actuators, things that cause this robot to move. And in addition, the genotype is going to have to encode neurons and synapses and all the other things that make up the neural network controller of the robot. Okay, so let's have a look at this genotype to phenotype map. Let's start by just looking at G. What does G actually look like? In this case, it is not a fixed vector encoding a bunch of floats. It is a combination of 4 lists. A list of vertices, a list of bars, a list of neurons, and a list of actuators. If we look at the vertices list, that list is a bunch of triplets, which encode XYZ 3D coordinates. If this vertex list has a length of 1, 2, 3, 4, 5, 6, 7, 8, it could be encoding, this list could be encoding 8 3D coordinates, which indicate where to place these 8 vertices. If a mutation adds a 9th coordinate to this list, that mutation is in effect adding a new node to this robot. If a mutation knocks out or removes a set of coordinates from this list, and in the child, the vertices list is now of length 7, that mutation is in effect deleting one of the vertices in this robot. So for now, imagine a population of Gs. Each one of these Gs has its own unique vertices list. Some of those lists are longer, some are shorter. They're encoding different vertices that are going to make up the different robots encoded by these different genotypes. So far, so good? Okay. You can guess now probably what the second list does. This list is made up of a list of quadruplets, 4 sets of numbers. Each quadruplet describes a bar. So it indicates, the first number indicates which vertex to start with, which vertex to end with, and the third and fourth number represent the relaxed length of this bar and the stiffness of this bar. Is that language sounding familiar to you? This third and fourth number are actually specifying some aspect not of the bar itself. Each of these bars is cut in half, and the 2 halves are connected together with a spring. Remember, relaxed or resting length of a spring and the stiffness of the spring. Greater stiffness means the 2 halves of the bar are connected with a stronger spring. A lower stiffness value indicates that those 2 halves of the bar are connected with a weaker spring, something like a slinky. Okay, so each of these bars, as this little arrow represents, can increase in length and decrease in length. The vertices and the bars lists together tell us how to take all of this genetic information and turn it into one part of P, one part of the phenotype, which is the body of the robot. So far, so good? Okay, let me jump to the 4th list here. This is the actuator. The actuators list. The actuators list is made up of a bunch of triplets. Each triplet indicates how to actuate that bar. So the first number indicates this actuator is going to be placed on top of this bar. Neuron index, this indicates, we haven't talked about the brain yet, but this second number indicates which neuron innervates or connects to that actuator. So in essence, the first two numbers say find this bar and find this neuron in the brain and connect them together. And the third number here, bar range, this